So now I have mentioned that we are in charge of what we want to render, and we should probably get rid of as much as possible from our scene before telling our operating system to color which pixel in what color and where to draw lines and so on. And the process to get rid of all the stuff that is not within our viewing frustum, which is not projected in a certain frame onto our plane, is called clipping. So the way clipping works is pretty straightforward. It's pretty hard-coded here. The purpose, as I said, is to eliminate the portions of objects that are outside of the viewing frustum. So for some reason, not only teapots are very popular in computer graphics as a test object, also cows. You'll see cows as frequently as teapots here. So for today's lecture, we basically work mainly with cows. So our view frustum consists of the boundaries of the image plane projected in 3D. So this is here the near plane, here we project to, and the far clipping plane, things that are too far away, too small, probably we also don't want to render. These are actually parameters you would tell the rendering system where you want these placed. They are always parallel to your camera. So if the red dot is not a camera, the camera would look the camera would look directly into this viewing frustum here. But the near plane, well, is of course our F. This is our projection plane, and then far plane is another parameter which just cuts off everything that's too far away. And then there are apparently 4 other planes, which are called obviously left, right, top, and bottom. It's very creative. So as a user, we can define as many clipping planes as we want. We could probably decide to clip off this corner here as well, or maybe we are rendering towards a very strange shape, so we would rather take a real cone. Maybe if we render into a circular window, and this is actually not that unrealistic. Think about VR glasses, and so they have a circular projection, so there you would probably use your clipping in a slightly different way. But for the traditional viewing rendering area, which is rectangular, we use these sort of viewing frustums. So why clipping? Well, there's also another reason. The reason is to avoid degeneration. So if we draw objects that are behind the camera, maybe objects where the camera would be inside at some point, we would also see parts of them, and the inside of these geometric objects are usually not that nicely modeled than the outside. Also, if you have lots and lots of small objects far away, this will lead to aliasing, a topic we will talk about in a couple of lectures. And you also want to avoid this. So we want to improve efficiency. I would say this is the most obvious and most important part of clipping. Now, when do we want to clip? So there are 3 options in what we know about the rendering pipeline so far. So what we could do is we could take this viewing frustum as it is with all its angles and so on, and clip out that part of our 3D scene in world coordinates. So we haven't done this transformation yet where we transformed into canonical view space. No, we just take it as part of the scene, of the overall scene, cut it, crop it off, everything, and then transform and look at this frustum. So we can just do this by using the equation of the 6 planes. It is reasonably natural. It applies exactly what I just said on the previous 2 slides. I could do the clipping also in homogeneous coordinates after the perspective transformation, after we are in canonically view space. We could also call this space then clip space. And before so just after we have transformed remember we can transform our coordinate systems so that they're aligned with my view axis, right? So we can transform this and then have all my 3D objects still in there. I haven't done the perspective transformation yet. I haven't done the perspective divide yet, the projection itself. So before that, I can just clip off in the 3D space whatever I want to clip off. So this has an advantage. This is canonically, it's independent of the camera. My clipping planes will be equally to the projection planes, always defined statically, constantly, within, at least relative to this coordinate system. The entire coordinate system, yes, I transform around and move around, but within that coordinate system, I can place that viewing frustum, and then it will move around with me whatever transformations I do. It's truly the simplest I can implement. It's also probably the same reason why I would implement the perspective transformation always within that canonically view spaces, because math gets so easy. The other option, the third option, is I could also do this within normalized screen space. So I can try to work my way back and then define within my screen space itself where this view frustum should be. That becomes reasonably messy, especially for objects in the plane of the camera and objects that intersect that viewing frustum. So it is possible, but it is reasonably difficult, and probably it has only be used for the painter's algorithm, another algorithm we will come about when we talk about depth in images. So for now, I would recommend that we do clipping in clip space, canonically, view space, camera space, eye space, whatever you want to call it. The space after you have transformed your always constant viewing space where your eye point is always in the origin to the direction you want to view your 3D scene to. Or the other way around, you transformed your 3D scene so that it looks like as if your viewing direction would look down this direction. So clipping itself relies on efficient math regarding half spaces. Half spaces are a really simple concept. It only defines spaces of geometric objects. There is, if you say you have a line or something, you can, at least in 2D, it's relatively easy here, you can always define to have an area on one side of that object and an area on the other side of the object. And you can just by definition say that everything on one side is negative, and the further away you are on that side is more negative, has a greater negative magnitude. And on the other side, the further away it is, it might have greater positive magnitude. Every point on the object itself, on the line here itself, is defined to be 0. So I can form implicit representation of that line by just saying something like x minus y plus 1. Here that's defining that line equals 0. So all points that fulfill this equation is 0. So this is my implicit representation of a line. You know this very well, but it also gives us an option to divide the space in any space into 2 areas. So each of them are half spaces, arbitrarily selected by choice. Everything left here is 0, everything right here is bigger 0. Everything left here is smaller 0, everything right is bigger 0. So in 3D it's becoming a little bit more difficult than doing this in 2D, and in 3D a concept you already came across comes in handy, which is homogeneous coordinates. And you know, you can define a plane equally with homogeneous coordinates just by, and spoiler alert, so I just can define the homogeneous direction vector of the normal to define an entire plane. So if I take the coefficients of an homogeneous direction component as A, B, C, and D, right, I get infinitely many solutions, but I can say this is also a representation of a plane. And then I can say, well, everything on one side of that plane is larger 0 and everything on the other side is smaller 0. So I can divide my entire real numbered space into 2 sides. Again, everything that's on the plane is 0. This is also an implicit representation of that plane. Now, so that plane equation, as I said already, that plane equation basically lives from the fact that I can define a plane by its normal vector. So the normal vector is this h. Okay, so this h is defined as a, b, c, d, which is any point, which is any normal vector on this plane in homogeneous coordinates. So this is the homogeneous direction vector. The d is not 0 here because, well, I could have it 0, but I can scale the whole thing to infinity. I'm not talking about unit vectors here. So this is just a normal vector to this plane. So each point x, y, z, and w has an infinite number of equivalent homogeneous coordinates. Yeah, so this is true for all homogeneous coordinates. All of them I can scale like this for any scaling factor larger than 0. So this really equates to an infinite number of equivalent plane equations. Okay, so I can really take this this normal vector and define an infinitely amount of normals for that one plane. So I can also abuse this somehow or make use of it by just scaling so that my directional defining components A, B, and C become normalized. So something like a squared plus b squared plus c squared equals 1. So I want that to be a unit vector effectively. And as soon as I have unit vectors, I can use things like the cross product, dot product quite easily without needing to consider scale all the time. Always remember, if you want to use dot product and cross product intuitively, then best to normalize your vectors also always before you do it. Otherwise, your result will always be skewed in scale, which is not right. So if you only want to work out if two vectors are orthogonal, then best normalize them and then do the dot product. Anyway, so having this vector, this normal vector here, I can use any point and calculate the distance of any point in my entire space. I can calculate the distance to the plane along the normal vector, right? So in the same direction as the negative normal vector. I can calculate the distance of the point to the plane by simply projecting that point onto the normal vector. So this gives me h dot p, which is all in homogeneous coordinates with a unit vector, and then I get assigned distance d for any point in my half spaces. And here I can define if it's positive, it's inside. So positive means in this case here at the same side in which the normal vector is pointing. And negative outside, I can say it's outside if that point would be on the other side where the normal vector is not pointing to, where the opposite of that area, then I can say, okay, this is outside, this is the negative half space of that plane. Okay? And now, you know, our Furing Frustum has simply 6 planes. So I can do 6 of these tests and say, if that distance, doesn't matter what the actual magnitude is, but if that distance is larger 0, I let it pass through the rendering pipeline and do all my projections and tell the operating system which pixel to render. Or if it's smaller 0, I just stop at that point, all operations, and spare the operating system all the work to render effectively nothing then in the end. In fact, I don't really need to do the trick from before and do something like this and normalize this vector and have a unit vector here. It's just probably good practice, because that gives this distance a meaning. It's really the distance from the plane. If you don't do it, you still get the right sign. So if you only need the sign, you could even spare the normalization step and just project on any scaled normal vector of that plane, and you would still get the correct sign, and this test would still work there. So if you want to clip with regard to this Furing Frustum, then we do it 6 times, and really just test 6 times if h.p is smaller 0, then we just reject that point, and we know the point will not end up on our Furing Frustum in our draw area. So now, how does this look like for the 6 planes we have? So basically, the near and far plane are trivial, right? The view plane, the viewpoint here, is always in the origin, and I know this point and I know this point, so I can just build from this plane, from the definition of the plane, going along an axis coming out of that viewpoint, I can just build the normal vector of that plane. So the normal vector is just the negative near direction here, right? So we're going, this is our coordinate system going through this here. This is y, this is x, this is z. So I'm just saying, okay, this is going 1 as z in this direction and is scaled by negative near, right? So we're scaling this to here, so that means that the negative just means that it points away from us. It points parallel to our negative z-axis, and it goes along 1. So if you plug in the numbers and plug in your coordinate system, you will end up with exactly this normal vector. Also for far, we do the same thing, but the opposite. So I want a vector that points towards me, -1, and scale it with far. So it's here on the far side of this viewing frustum. The others get slightly more complicated, but not much more. So if we just work out the bottom, for example, for the bottom, we also know that we have these points here. We have the points. We know the corner points of our viewing frustum, and with the origin together, we can actually work out a plane here. So for example, for the bottom, I can use this plane here. Okay, so this entire plane. And by using the cross product of, say, these two here, I get a vector normal to this cross product. So assuming a direction like this, going away from the eye, build the cross product with these two, then this gives me the normal vector for one of these planes. Same the opposite direction for the top and the left and the right with these planes around, and we get the equations, the homogeneous representation of these plane normals. So here is just how you plug into the cross product formulation of left bottom near, right bottom near points. So these are the points here. This is right, left bottom near here, right bottom near. So this is left bottom near, this is right bottom near. So I only have these 2 points. The points are at the same time the vectors inside the plane I'm interested in, because this is the origin, right? So I can just plug in these point coordinates directly. That's what makes it so nice to have it in canonical view space, right? It makes it quite straightforward. And then just work out through the cross product what my actual values are, what my actual values for each bottom are. And they are, in this case, are 0, near, minus bottom, and 0. So this is my homogeneous representation. Okay. So something that might also happen in clipping is that you have an object, a line, which crosses one of your clipping planes. So it goes, you need to clip lines, for example, into segments, or triangles into segments. This gets slightly more complicated then. Effectively, what you use is just the explicit parametric line equations here and your parametric plane equations, and plug the one into the other, right? This is set them equal, you get the intersection point. And you need to do that for all of the objects that you intersect with your clipping planes. You can do that more straightforwardly by using the normal vector. So you can either set the one equation into the other, then solve the linear system of equations, or you just use the normal vector and do the projection dot product trick from before. So one method would be for any vector v lying in the plane n dot v, we know that n dot v equals 0 must be true. If we use the explicit representation of our plane, then we can define the intersection point as mu p1. So p1 is here, p0 is here. These are the line segment points, and p is our intersection point. Okay. So we can define mu p1 plus 1 minus mu p0, right? We go 1 in this direction, and negative our scaling parameters in this direction, and then intersect the plane. So we choose then v to be any point on the plane. This can be right top, near some of these kind of corner points. And then we can say a vector in the plane, any vector in that plane to that point is given by mu p1 plus 1 minus mu. So this is the part from above, the parameterization, minus v. All right, so this is a vector, just a vector in the plane, but we know that this vector is inside the plane. So if I calculate now the normal vector, which I know, n dot my line equation here, so this vector in the plane, then I know that this is n dot v, this is n dot v, this is v, must be 0. So I can solve this for mu and find the point of intersection by just then plugging in and say mu times p1 equals our intersection point. So this is our intersection point then, and from it's my new line segment then, and I then just start my line segment at this point. So there are four different tests or 4 different configurations here, which I would need to test in this context. So if my normal vector dot p is greater 0 and the normal vector dot q is smaller 0, so you have p and q, so one point and the other point. If one is larger, if one is on one side and the other one is on the other side, then we have to clip q to the plane. We have to do this line intersection from q and go mu times q or p times here. So we basically move q here. If the other case, if it's the other way around, I have to clip p to the plane. If both are on one side, so if the entire line segment is on one side, I pass it through this particular plane. And if both are on the other side of that plane, I clip them completely out. So this is basically the entire process, and I have to do this 6 times for all of these clipping planes. Interestingly, this kind of more elaborate process to clip off all of these objects for your, I don't know, thousands of objects in your scene is still more efficient than transforming your entire scene with all the objects that are not visible and then just throwing this at the operating system. So this is relatively elaborate, but the advantage is that these kind of operations are always more or less straightforward and linear. So what you can do, and what is done currently really, is that these operations are implemented in hardware on your GPU. So they are less expensive than they sound here. And it's really reasonably dumb and straightforward algorithm. Just clip everything against every 6 faces and then move these components, and you get a kind of new set of positions and representations that then pass through the final stages of the rendering pipeline. So clipping can be carried out against any object, not just the viewing frustum. And really what it is a containment test. Okay, this is also a occasionally occurring exam question that one can clip against an arbitrary object, and then the whole thing becomes really a containment test. And there is 2 things we need to distinguish. One is containment with convex objects, the other one is with non-convex, concave objects. So convex polyhedra is a very common problem. A point inside test, this is something you'll come across in this lecture quite often. For convex objects. Concave objects, this is harder. It's you don't need to memorize by heart all of the steps that are required to do it with concave objects, but they're also kind of straightforward, at least things like containment tests. Checking if something convex or concave is a related problem. So slightly more difficult for concave objects, but well, let's see how this works. So there are 2 definitions of convex objects. One is a line joining any 2 points on the boundary lies inside the object. So I have a concave object, and if I take any point on the surface and connect to every other point of that object, then the entire line will always be inside of the object. That's a concave object, a convex object, sorry. And the other definition is the object is the intersection of planar half spaces. Right, so if I put half spaces together in any configuration, this will always be a convex object. Will always be a convex combination. So something like this. Here I've just cut off a corner of a cube, but this is clearly a convex object. So how do you test this if an object is convex? Well, there are basically algorithms that look exactly to what we have just defined. You take every corner point of your object, test it against every half space, and if the tests from before, so if everything lies on one side of all of the half spaces and always on the inside, then your object is convex. So this works due to to our definition 2 here, so to the combination of half spaces, right? All of the objects, so all points of the object must lie entirely on the side of on one side of each face. So they must always be kind of all contained inside. So you, of course, you don't do it densely for all the points. You always do it for the kind of extremer points, the corner points of your object. And if it's fulfilled for those, you can prove that it must be fulfilled for all of the points inside. So this is the containment test as you can implement it. You would probably, in practice, to make it more efficient, you would probably do it with a vector formulation, because then again you can use the dot product to project things. So this really avoids the need to calculate the Cartesian equations for all of your half space planes, and we store really only the normal vector for our plane. So that makes life slightly easier if I just take every point of every corner of the boundary of this object and project it on every normal vector of my planes, then setting these equations equal and really doing the explicit plane equation versus explicit line equation. So this is how this could look like in vector formulation. If I want to check if this point P is on the one side or the other side, so the inside or the outside of that convex object here, right? So that is just a face of my convex object. If I want to check if it's on the inside, so if this vector here, so P minus A is just any point on my plane. So that could in fact be any of these corner points as well, which is what you would probably use in practice when you implement this. So if a vector between my point and any point on the plane and the same point and the normal vector is, if this angle here between is acute, then you know it's inside. Think about it, it's quite reasonable. Yes, then they point almost into point almost into the same direction, so it should be inside. So this is an acute angle, and then if they point in the other way, then there's not an acute angle. So it should be look in the other side. So it should be outside. Okay, so how do I test this? How do I figure out if this angle here is an acute one or not? And we do this via the dot product. So, and we know that an acute angle means that cosinus theta is larger 0. So if I do the dot product here, so cosine is the dot product basically, just scaled. So if I do the dot product, this projection, and project the vector P minus A, so project that point relative to the plane on the normal vector. If this is larger 0, then I know that this angle is acute, and then I know that that point is inside of my object. So I only need to do these projections, and if all of these tests with all of the faces succeed and they are greater 0, for example, then you have your containment test basically. Okay. So this vector formulation really does not require us to find the plane equation of the face. We really only need the normal vector of the plane. And the same thing is really true also for the plane, because really we only need this part here. We only need this normal vector here, n is equals ABC. So how do I find the normal vector of any convex object of any plane? Well, really all you need is just 2 vectors in the plane. If you have an object like this, well, you would probably just use the edges of that object. And if you want, for example, at that node, your normal vector, then you build a cross product between these edges. And now some of you might think, well, yeah, but this depends now how do I define these vectors? Do I say this point minus this point, or this point minus this point? And this is quite important, because this defines if you go clockwise or anti-clockwise around this object. And this defines then clockwise or anti-clockwise defines if your normal vector will look in this direction or in the other direction. Right? So this is a common problem in graphics. If you design something and you lose your normals, it's not that trivial to recompute your normals. you need to correct some of them by hand just because of prior knowledge. But as long as you're kind of consistent with being clockwise or counterclockwise around your objects, you should end up with predominantly with normal vectors that predominantly point into the same direction. So yes, so how do I check now if that normal vector is actually the normal vector I want? I need the rest of the object. So if I have other faces of that object, what I would need to do then is to check with another point of my concave or convex object here in this case, if that angle is again pointing inwards. If I want the inward normal here, for example, if I want it to point inward, then this angle again needs to be acute. So I build with any other point inside of that convex object the dot product, and if this is larger 0, then it's the inner surface normal, if I'm after the inner surface normal. And the opposite of this, of course, is then the outer surface normal. Okay, have a look at this problem break if you like. There are also the tutorials which will contain similar.
Good morning. Good morning.
Okay, let's quickly talk about the same thing for concave objects. So really containment and clipping can be carried out with any sort of objects, as a concave objects, and most algorithms really are based on something called the ray containment test. And the way this works is that I find all intersections between a ray and the polygon edges, and I can just define whatever I like as the ray, so ray pointing in any direction. And then the test is very simple. If the number of intersections is odd, the point is contained. But I need to intersect that ray with every single edge here and edge segment here, line segments in fact. So I need to check if all of this is contained. So this is basically how I do concave containment tests. So how do you calculate the ray line intersection? So rays have pretty much an equivalent representation to lines, but they only go in one direction. So if you rays here, so this is ray, just goes in one direction here. So I can say that for test point t, a ray is defined as t plus mu and the direction. So I have t is here, and then I have mu times a direction somewhere, where mu is a scale factor, a scale parameter larger 0. So we choose a simple to compute direction as ray. I can choose whatever I like, remember, so I just choose something 1, 0, or in 3D 1, 0, 0. That's good enough. And then I try to intersect this with my line segments. I really need the line segments between V1 and V2. So I plug in my P somewhere here is V2 plus another scale parameter here times the vector between V2 and V1. Okay. So ray, as defined before, is T plus mu D, which in this case is 1, 0. So I can just plug that in, put these two equal, calculate it, solve for eta and mu, and then I have a valid intersection if mu is larger 0 and if the eta is between 0 and 1, if it's somewhere on that line segment. And I can also use the mu, for example, to move from my point to that intersection point, and I have the exact intersection point. So that ray test is not only valid in 2D, it is also valid in 3D. If I use a ray that is projected in any direction, and if the number of intersections with the object is odd with the object, so I have now half spaces, planes, then the test point is inside. It's more computationally expensive than if I know already it's a convex object, but this is the more kind of general form when I count intersections and then have a test like this. So I first need to compute the intersection of the ray with the plane of each face, yeah, and then if the intersection is in the positive part of the ray, so mu larger 0, then I need to check whether the intersection point is contained in the face, not just in the planar extension of the face, right? So if it's inside that quad here, not just somewhere here, So if it's inside here, so that all checks, 4 checks here, I need to check if it's all inside here and if it's intersecting here, lots of computations, but with that I can clearly define if a point is inside of the object. Well, unfortunately, the plane of a face does not in general line up with the Cartesian axis. So the second part is not a 2-dimensional problem. You have to solve this in 3D. However, containment is invariant under orthographic projection. So if you use an orthographic instead of perspective projection, so you can simply reduce this to 2 dimensions in that case, but only if you use orthographic instead of perspective projection. And yeah, clipping, I can also use clipping to any sort of concave volume. So the only thing I need to do is to find every intersection of the line to be clipped with the volume. So I need to now result in several line segments here and then divide the line accordingly. I can also do this by, so this I basically can only do by splitting the volume into convex parts and then count how many convex parts I have and then run the convex clipping algorithm on all of the objects I have. So you see this is becoming very, very expensive, and you probably wouldn't have a concave clipping volume except for very, very special applications, which honestly I can't think of any right now. Probably post in the comments if you have a suggestion for a use case scenario where you would use a concave clipping volume. Yeah, these are the cutting planes here. So here I know there are 3.